Hi, I'm Officer Zacal Jr. and I'll be reporting about inductance. Now, what is inductance? Inductance is the property of an electric conductor or circuit that causes an electromagnetic force to be generated by the charge in the current flowing. Well, for example, we have here a coil, two coils rather. The small coil in the inside of a big coil. So both coils have a current passing through them. So if those coils be merged together, or merged, there would be voltage. There would be a voltage created in it. So that's more of a definition of what inductance is. So the magnetic flux serves as related to the current in the circuit and other circuits whereby, meaning there is a voltage in any circuits, in any other circuits. So yeah. For a coil carrying current I, there is a magnetic field produced around it. The value B at H2. Therefore, the magnetic flux through the coil is also proportional to I. So we have here the formula of inductance, where MO is the permeability of core material. We have here the N1, which is the number of turns in a coil. The N2, which is the number of the turns of the second coil. And then we have here the I, which is our current, and last is we have here the A, which is the area or the cross-sectional area, wherein N is equal to N over N, where N is the number of turns in a wire over N, which is the average length of a coil in meters. That will be all.
Faithtrex Brigole, and today I'm going to explain about mutual inductance. First, mutual inductance, if two coils are placed near each other in the same plane like this, a changing current in one coil will induce an EMF in the other coil. From the Faraday's law, the EMF E2 induced in coil 2 is proportional to the rate of the change of the magnetic flux passing through it. For example, if this is the two coils, the line 1 and this is the line 2, if this coil has voltage, then the line 2 will induce the voltage of this one. So let B the magnetic flux in each loop of coil 2 created by the current in coil 1. If coil 2 contains N2 turns, there is the total flux in coil. Here is the formula in getting the mutual inductance. In here, I will not explain this formula anymore because at the end of this PowerPoint presentation, it will going to be explained by my groupmates. So, mutual inductance of coil 2 with respect to coil 1 is constant and dependent upon the geometry of the two poles. The reverse equation can also take place when a charge and current in coil 2 induce an EMF into coil 1. So, here are the formula in getting the mutual inductance.
Self-inductance. The concept of inductance is applied also to a single isolated coil of N turns. When changing current passes through a coil solenoid, a changing magnetic flux is produced in coil. In this turn, induce the EMF in the sum coil. This EMF opposes the change in flux when this is the Lenz's law. Lenz's law and self-inductance. It can be seen from a formula that the voltage induced by a change in current is in the opposite since the change in current Any current induced in a conductor will opposite the change in current that caused the change in flux. Lenz's law states that induced electromotive force, EMF, gives rise to a current whose magnetic field opposes the original change in magnetic flux. Self-inductance. The magnetic flux passes through n turns of the coil proportionally to the current n coil. This proportionally is called self-inductance.
I am going to discuss the continuation of the topic, self-inductance. So, when the current passes along a wire, and especially when it passes through a coil or inductor, a magnetic field is induced. This extends outward from the wire or inductor and could couple with the other circuits. However, it couples with the circuit from which it is set up. And when the current in the coil changes, this causes a voltage to be induced or to produce in the different loops of the coil that results self-inductance. The thing is that when the current in the coil is increasing, the self-induced EMF produced in the coil will oppose the rise of the current. That means that the self-induced EMF is opposite of the direction of the applied voltage, and when the current in the coil is decreasing, the self-induced EMF will have the same direction to the applied voltage. That's all.
Good day, I am Mae
Ay, so wait, Sige, go na.
Okay na? Sabi, nakalimot ako sa akong
Sige,
story.
ikat lang din.
Good day, I am Mae Virtudazo and I will give you an example about mutual inductance. So here's the problem. Suppose that two insulated wires are wound into a common cylindrical former of length 0.1 meter and a cross-sectional area of 0.05 meters squared. The number of turns in the first wire is 100 and the number of turns in the second wire is 300. What is the mutual inductance of the two wires? So we have this following formula. M is equals to the mu of R times N1 M2 times A overall divided by the length. So MO stands here as the permeability of a core material and N1 M2 stands here as the number of turns and area is the A is the area of the cross-sectional. Length is the length of the wire. So plug in this following data, we will get 0.0188 Henry. And the next question is, if current I flowing in the first wire increases uniformly from 0 to 10A, what EMF generated in the second wire? So we have this following formula. EMF generated in the second wire is equal to the negative of inductance times the change of the current over the change of time. So plug in the following data in the formula, we will get negative 1.88 volts. Note that the minus sign indicates that this EMF acts as to drive a current in the second wire, which circulates in the opposite sense to the current flowing in the first wire in accordance with Lenz's law.